Hey everybody, Mr. Smith here, and in this video lesson, we're going to talk about the interference of 2D waves. So let's get started. So to start off, I wanted to make a couple of notes about interference and some terminology that we'll be using today. So on your lesson sheet, on your lesson sheet, I'll go back to that slide in a second. You've got a large visual of a 2D interference pattern. So we're going to talk about, I'm going to have an even bigger one of these, and we're going to do some labelings on it and stuff like that. But the bottom part of the diagram, like right in everything from like here down, this is even on top of the diagram, that's a space for you can take notes there, okay? So you got a big space to take notes wherever you see fit. We're only going to be making use of the diagram on the upper half. So having said that, let's chat about interference a little bit. So first, some terminology. So when looking at a wave, I'm going to refer to, I'm just actually going to add a little bit more here. So I'm going to be referring to these maximums as a crest and these minimums as a trough. So maybe you used similar language in your grade 11 course, maybe just a different peaks and valleys or something like that. For this lesson, I'm going to use crest and trough. And if you actually didn't get to cover this stuff in your grade 11 course because of the school closures, then you can just, we'll use crest and trough. And then in a diagram like this, you can think of the wavelength several ways. You could think of the wavelength of this wave being from crest to crest. But if I add another little bend there, you can think of the wavelength also being from one trough to another. It would give you the exact same wavelength. So that's some terminology we'll use. And ideally in your grade 11 course, you looked at what happened when two waves interfered with each other. So and this is called interference. So let's say I have one wave there and I have another wave that has the same wavelength, but it's just, we'll say, out of phase by half of a wavelength. So it's just like shifted over. People who have taken some grade 11 math will be familiar with the idea of a phase shift for a periodic function. But in grade 11, you guys learned a principle of interference, the principle of superposition, that you can actually basically add waves together to get a resulting wave. And if you add two waves like this that are kind of perfectly balanced and out of phase, the crests and troughs line up. The crests and troughs line up. All of them do. And the two waves meet where there's no amplitude at all, where the wave is kind of in the middle. And the result is when you add those two together, you get nothing. It's like those two waves perfectly cancel out. And when these two waves perfectly cancel out, we get destructive interference. And that occurs when, I want to emphasize, when a peak meets a trough, we are going to get these perfect destructive. So anytime there's a perfect balance, right? Above, below, destructive interference. What we can also have is if those two curves line up with each other, if those two waves line up, so maybe just something like this, just because if I draw them over top of each other, you won't be able to see them. But if those two line up, then the amplitudes will add, and the two crosses will build on each other, the two valleys will build on each other, and so you get a wave that is kind of this, goes above and below the same point, but its crests are twice as high and its valleys are twice as low. So something like that, and we call that constructive interference. So we'll consider everybody kind of caught up. We'll be making use of that terminology in our lesson on these 2D interference patterns. All right, so move on. So we talked about diffraction in our first lesson. I'm going to erase these things. Actually, I don't think you need to erase them. And again, now you can be taking notes below this diagram. We talked about how when you shine a plane wave through a very narrow slit, you can think of it becoming a circular wave. And if we have two narrow slits, so you can think of that being source 1 and source 2, then we get two circular waves coming out. You could even think about this as two faucets dripping water at the same rate. So if they drop water at the same rate, they'll have identical circular waves coming out. And eventually those waves are going to meet each other and interact and interfere. And so we want to today quantify some of the relationship between how those waves will interact. But this is a very specific pattern. And there's three conditions here that we need for this pattern to happen. So the first is that the point sources have to have constant frequency. So it's like drip, 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 drip. They have to be constant frequency. So dripping at the same time to produce these identical ripples, right? These two identical circular patterns propagating out from source 1 and source 2. So same frequency. Note that this also gives the same wavelength of waves and the same speed of waves. So constant frequency. You have to have constant source separation. So the two sources, S1 and S2, whether that's a dripping faucet or whether that's two narrow slits you're shining light through, they can't be changing distance. They're fixed in space. And so they're fixed in space, drip, 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 same spot, constant source separation. And the third point is the sources are in phase. So it can't be like drip, 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 drip. They have to be drip, drip. It has to be the same frequency to produce this pattern. So those are the three conditions to get this pattern. And now we're going to talk about this pattern in more detail, and then we're going to add some things to your diagram. So I've got it blown up here. All right. So, and I may keep coming back to this slide, kind of just jumping back and forth. So the first thing is this is like a top-down view of a 2D interference pattern. So think of it as like a top-down view of like two dripping faucets with the water waves rippling out. And you'll notice that some of these circles have dashed lines and some of them have solid lines. Because you can imagine these water waves are going to have max and mins, right? Crests, I combine that into one word, crests and troughs. And so we represent the solid lines represent the crests of a wave. And the dashed line will represent a trough. Okay, so everywhere you see a dashed line, this dashed circle is just a big circular crest for this wave moving outwards. So that's what those mean. A second thing, and I'm going to label this over here somewhere where I have room. But the wavelength of these waves. Remember, wavelength can be measured crest to crest or trough to trough, or other ways too, but those are the easiest ways. So the wavelength would be like the distance between two solid lines. Anywhere on the diagram, it's the same wavelength. No matter where you go, if you're closer to the source, if you rotate around the diagram, you get the same wavelength. And that also is the same as, maybe I'll draw this one here. The distance between two dashed circles is also the wavelength. So that's what the wavelength represents on that diagram. So crest to crest, trough to trough. What else do I want to label on here? Okay, we are ready to talk about nodal lines. So I'm going to, okay, we'll go to the next slide in a few minutes because I have some more things to add here. So remember in our previous slide, we talked about that two slides previous, when a crest meets a trough, the two waves will kind of cancel out, right? So what's going to happen when we have these crests, solid lines, meet a dashed line, a trough. So when a solid line from the first wave meets the dashed line from the second wave, those two waves are going to cancel out, and we'll basically get like flat water. And this is going to happen at a bunch of specific points. And I've drawn on here a bunch of points where that happens. So these dots we call nodes. And as you can see, they kind of form nodal lines. Hey, buddy, you did some drawings for us? Hey, thanks. Okay, this is the first time at the 50th lesson, kids stormed in. What? A, B, C. Okay, you wrote the alphabet. Yeah. Okay, very good, buddy. Okay, can you close the door? Thanks, I'll be done in 10 minutes. Yeah, it's bound to happen one at a time this summer, guys. You'll probably come back again. Okay, so where was I? So every spot where a crest from one wave meets a trough from another wave, they're going to annihilate. And we get these nodes where we have destructive interference happening. And you'll notice that these nodes, actually, there's like a pattern. They occur along a line. And if you drew even more concentric circles within, you'd actually get like maybe more circles in between. But that's enough to visualize. So, and you'll notice they form lines. Now, actually, I have drawn the second and third nodal lines on each of these, on each half. There's actually another set of a line of nodes between that central axis and moving outwards. So what I love is, can you draw little circles on your diagram for nodes for the first nodal line? So this is, I'll label on here. So we would consider this to be the second nodal line. So it's a line of nodes. And this one is the, is this one the third? Yeah, this one is the third. But there is one in between n equals 2 and the dashed line. So if you want to pause the video and try adding those nodes in now, draw the first nodal line. I'm going to do that. So unpause when you're ready, but I'm going to carry on with that. So every time we see a solid line and a dashed line, destructive interference, we add a node. Destructive interference, destructive, destructive, destructive. And it's neat. They kind of form a straight line. Now this is my colleague at work made this diagram. So it's a very good diagram, but it is just it is like not a perfect diagram. So they might not line up perfectly. And I want to stress too that these will not be in the real world. These won't be perfect straight lines, but they're near enough straight for our analysis. So there's our first nodal line, and we get another nodal line on the other side too. We just call it the first nodal line too. So because of the symmetry, we don't say, hey, the nodal line to the left, nodal line to the right. We just say the first nodal line. So n equals 1, n equals 2, n equals 3. So we've talked about nodes. We've talked about nodal lines. The next thing we want to do is think about, so how can we quantify where those nodes occur, where that destructive interference happens. So on your diagram, I want you to label what I'm bringing up here. So I just picked out a node on the first nodal line. So I got it there in orange. And let's call that P1. So we've got source 1 being, we call it S1, source 2, S2. And I just have that point in space there, but it's on a nodal line, P1. So that's a spot where we're going to have some destructive interference. And we want to ask ourselves, well, what do I know about, what can I say about the difference between the time it takes away to get from S1 to P1 or from S2 to P2? So I have a line here, and you should maybe even use a ruler when you do it, just to get a really nice, clean diagram. The length of that line, the distance that wave travels from source 1 to P1, we're going to call that P1 S1. And you can see, because it has to cross that center axis, it's going to travel farther than the line from S2 to P1. The distance that other wave travels, we're going to call P1 S2. And hopefully you're convinced that the one on the left, P1S1, has to travel farther to get to P1. So they each travel a different distance. How can we quantify what that path difference is? So this is everything I want to add to our diagram. Actually, that's a lie. There's one more thing to add to this diagram. We're going to call the slit separation D. So D is the distance between S1 and S2. And then I think, yeah, everything I've got, yes, that's all I wanted to get. All right, so we have this diagram. Now I might come back and talk about this diagram a bit, back and forth. So let's add some notes here. So first, destructive interference, those nodal lines occur when a crest meets a trough. So I've said that many times now. You might want to get it onto your note. Now, this is a point we haven't talked about. When destructive interference happens, what must be true at the waves? They must be out of phase by half of a wavelength. So I'm going to go all the way back to this diagram here. So think about the wave I drew here with the crest and trough. If I want to make them out of phase and I wanted them to have if I want them to completely have destructive interference, then I need to take my crest and put it where a trough is, right? So if I want destructive interference to happen, I have to shift this wave over by half a wavelength, lambda over 2. And if I do that, I get this wave, and then they're going to interfere. So that's the big idea. If you want destructive interference to happen, the two waves have to be shifted by half a wavelength. That's a really big idea. Pause and let that digest for a second. Hopefully you're convinced. So everywhere we have those nodes, all along every one of those nodal lines, destructive interference is happening. And that means that the two waves are out of phase by half of a wavelength. And they become out of phase because one wave is traveling farther than the other. So they will likely look different when they'd be at different spots in their wave function as they get to that point. So they become out of phase because one travels further. And now we want to ask, how can we quantify the difference in those two paths? What's the difference between P1S1 that length and P1S2 that length? Well, it depends on a couple things. So as we talked about, it depends on the wavelength, and it depends on which nodal line you're on. So let's start getting that down. So let's talk about the path difference. The path difference is what we're going to call the difference in distance that each wave travels. And again, it depends on the nodal line you're on, and it depends on the wavelength. So let's talk about the first nodal line. What's true everywhere on the first nodal line? I'll actually go back and then we'll come back to that one. So first nodal line, n equals 1. So look at source 1, guys, and let's just count the number of wavelengths to get to, let's actually use P1 here. So from the source, count the solid lines. One solid line, so one solid line, two solid line, 3, 4 and a half. 4.5 wavelengths to get there. I'll just jot this out to the side. 4.5 lambda. And let's do from source 2. 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelengths, right? Remember, they're going to be off by half a wavelength. 4 wavelengths. And everywhere along that line, the path difference will be half a wavelength. And you can try it for yourself. So look at this first point here, guys. 1 wavelength, 2 wavelengths, 1.5 wavelengths. Everywhere along the first nodal line, the path difference will be 1/2 of a wavelength. But look at the second nodal line. So I might go I'm going to go talk about this point here. So let's look from the first source. We have 1, 2, 2.5. So we can run the second, so 2.5 wavelengths. And then from source 2, 1, 2, 3, 4. So 4 minus 2.5 is 1.5. And on the second line, we're 1.5 wavelengths away. And then the third line will be 2.5. And the fourth line, 3.5. But there's this pattern there. And so let's get that pattern down right here. So we've talked about what the path difference is, and now we're going to get the math down. So on the first nodal line, we just talked about, so I'm going to get this down, then we'll talk about it. The difference of these two paths, P1S1 minus P1S2, and we use the absolute value signs because P1S1 might be shorter or longer depending on which side of the central axis you are. So by using absolute value, it doesn't matter which side we're on. That difference in the two paths is half a wavelength. We just proved that on our diagram. And the second nodal line, so this is a point on the second nodal line. So we'll call it P2S1 minus P2S2. We talked about is 1.5 wavelengths, 3 lambda over 2.
Ooh.
Oh, Asher, we're doing a video, buddy. Okay. Okay. Can you give me 5 more minutes?
Walk, walk.
Asher, can you give me 5 more minutes? I'll be right there. Sorry, guys. But yeah, we got through 50 lessons without it, so it's bound to happen. We'll just roll with it. The third nodal line, this is the last one we'll get down before making a general statement. So if you take a point on the third nodal line and you find its path difference between the two sources, it will be 5 lambda over 2. So again, this is like 0.5 lambda, 1.5 lambda, 2.5 lambda. So you can see the pattern, but we don't want to write this like out a million times. So we'll say in general, on the nth nodal line, we get this pattern. So a point on the nth nodal line, the difference, the path difference between that nodal point on the nth nodal line from source 1 and source 2. So for the first, it was half. For the second, 1.5. Third, 2.5. So it's always like a half of a wavelength below n. So the formula is the path difference is always n minus 1/2 times lambda. And where n is the nodal number. So that's the equation for what we call the path difference. And that equation will hold anywhere where you have a nodal line or destructive interference. And just to actually, do I have the applet still running? Let's see if I do here. Do I have? I don't have it still running. But I do have a video. I do have several videos posted for today, actually. Where's our slideshow? There we are. And one of them is from Veritasium doing making a 2-dimensional wave interference pattern. And you can see that all along the nodal lines, you just have these lines of calm water. And this equation will be true for all those lines where it's calm, where there's basically no wave. We have destructive interference. So we're going to do a couple examples. Now, these examples actually work best if you can possibly print them off and measure things with a ruler. And that's what I would do normally if I was teaching this in a classroom, which I normally do. However, we're just going to make the best of it. So if you actually, it doesn't really matter what values you use, as long as it's just the concept of doing the question. So if you have this printed off, great. If you don't, just draw a diagram like this. It doesn't have to be any certain measurements. Just draw it on a piece of paper, and we'll walk through how to calculate the wavelength using this 2D interference pattern. So here we have a point, and now I've made a point of saying here that this is on the first nodal line. Okay, so we know that n is equal to 1. Okay, and I'm going to draw a line from there to there. So that is our P1S1, and our line from here to here, that would be our P1S2. Now, if you've printed it off, that's great. I'd like you to measure the distance in millimeters from P1 to S1, and then in millimeters from P1 to S2. You can pause the video and try that. And if you're just copying out the diagram, do the same thing. Get a ruler, and for what you made, measure those two distances. Now, I'm going to share the distances I got when I printed this out. I got 77 millimeters and 69 millimeters. So if you printed this out, you should have the same thing. If you did just copy this down, you'll have two completely different values, and that's okay. I'm going to show you how you can get the wavelength from these two path differences. Because we know on the first nodal line, the difference in these path differences is exactly half the wavelength, right? So let's set this up. So we know that P1S1 minus P1S2 is always half the wavelength. And again, this is the equation for when n is equal to 1. And we know that because we're on the first nodal line. So P1S1 was 77, P1S2 was 69. And we know that's equal to half the wavelength. That gives us 8, and the absolute value of 8 is 8. So 8 equals lambda over 2, and we get lambda being 16 millimeters. So this is neat. You can measure the wavelength. If you're unsure about the wavelength of the source you're using, that you can find it by analyzing path differences. That's pretty cool. Can you guys try the following one? So this is a similar example, but this point is on the second nodal line, and it's kind of hinted that, called it P2. So again, if you've got this printed off, you're going to have the same values as me. If you are just copying it down, you'll have different values, but that's okay. You're going to estimate the wavelength for your pattern there. So we're going to have P2S1 over here, P2S2, that distance over here. And we know that on the second nodal line, we're going to have, I'll use decimals for this one. If you like 3 over 2 lambda, good. If you like 1.5 lambda, that's good too. So again, make your measurements, and if you're printed it off, you'll get these values I write down. But if you're using your own, follow along with the process, and you'll get the wavelength corresponding to your diagram. So P2S1 got 99 millimeters when I printed it out, did it on paper, and I got 77 millimeters. And again, my hope is that you've paused the video and like tried these on your own. And so we have the path difference is 22 millimeters. There's a 22 millimeter difference in the distance each wave traveled to get to that point P2. So 22 equals 1.5 times what number? Well, now we can just divide 22 by 1.5, and about 14.7 is the wavelength. All right. So what should you be able to do after this lesson? You should now be comfortable with this 2D interference pattern and understand that the 3 conditions that make this happen: constant separation D, same frequency, and in phase. This will produce this 2D interference pattern where you get these nodal lines where a crest meets a trough. In terms of water waves, this would be lines of very still water. And we know, and you'd expect to know that the path difference is you're always going to be off by half a wavelength, or adding a wavelength to that. So a half, or 1.5, or 2.5, and it depends on which line you're on. Line 1, it was half a wavelength. Line 2 was 1.5. Line 3, it was 2.5. And so all of our work kind of led up to this path difference equation. And you should be able to use that path difference equation to, given the nodal line and a point, find lambda. Or maybe if I gave you the lambda and other information, find out what nodal line we're on. Or possibly if you had information on both of those things, maybe find something about the difference from the path length from one source to a point. But you should be able to use that equation. What are we did these examples, and what are we doing next? Up next, we're going to imagine shining light through two narrow slits. So right now, you could have just thought of what we just did as maybe two water waves and thinking about what would happen, what interference pattern would we see. But now we're going to shine light through two narrow slits. If the slits are narrow enough, it should create a 2D interference pattern like we've just discussed. And we should start to be able to predict where destructive interference would happen. And guys, for light waves, what do you think destructive interference would look like? It would look like darkness. So we should start be able to predict if we shine light through two narrow slits and everything interferes and we have some constructive interference and a lot of brightness and destructive interference, darkness, those nodal lines where darkness should occur, we should be able to predict where they should be, get an equation predicting where they should be. And if we can get this equation, we can actually start doing experiments where we can see, hey, we've predicted light should obey these 2D interference patterns. We've got the equations, did the math, and they do. And we can come to a conclusion and saying, hey, we have a good reason to believe that light is a wave because it follows these predictions from our 2D wave interference patterns. So our final lesson is going to have a big derivation. Just going to get that out of the way, let you guys know. It's going to be a big derivation, but the payoff is going to be great. We're going to have Young's double slit equation. But until then, have a great day, guys. Stay well. We'll see you soon.